we now have sufficient background information to begin consideration of what constitutes the minimal specification of a quantum state. And the way we are going to explore this is actually through we're going to use a thought experiment. Now, the nice thing is that we don't actually have to do the actual experiment, because all of the lessons that we've buried into our de Broglie hypothesis tell us what the results of this thought experiment are going to be. Our goal, though, is to use this particular situation to tease out of the de Broglie hypothesis the formal structure of the quantum theory that we're going to be using moving forward. So it takes a little while to set up the details in this thought experiment. We will set them up first and then begin to explore their implications. And these are going to be some fairly deep implications. So we will begin by setting up some axes, and you will see that for the reasons that will become clear in a moment, I'd like to make the x-axis my vertical axis, and for now I'm going to leave the horizontal axis just unspecified. So I'm going to have a coordinate system like this. And then what I'm going to do is I'm going to shoot particles towards the origin, all coming out of a special source that I'm going to use. So let's see if I make one of my sources, right, where I try to prepare particles in a pure state. So this is going to be a source that spits out particles of a single energy. So it's a source of pure energy, of particles, okay, of particles with pure energy E, which then tells us, at least we know the magnitude of our momenta of these particles is square root of twice the mass times the energy. And I'm going to have these particles directed, generally speaking, towards the origin. But of course, they do provide some spread here. I'm going to be at some distance, actually, from the origin, capital R, which eventually I'm going to make large. So they hit somewhere around the origin. The key point, though, is they are directed toward the origin at an angle, which I will call theta naught. Very good. Now, what happens with these particles is just before they get to the x-axis, I put a blocking filter here, right? So I'm trying to make a filter, right, like so. So this is here, I'll label it over here. Give me more room for my diagram. That's a blocking filter. And the idea between that about that filter is it mostly blocks the particles. It's characterized, though, by a transparency that looks like this. So there's zero transparency when I'm far away, right? Right, so particles don't get through up here. Then there's a nice continuous smooth transparency function when I'm near the origin here, and then it goes back down to 0. So that really particles only get through in a fairly narrow, but it doesn't have to be super narrow, but a controlled distance here, sigma, right? And then the particles then get through that filter and then make it down to my x-axis. Now, you will notice this is basically like a slit, but I've made it a nice continuous sort of a slit where more particles can get through in the middle, and then continuously the slit kind of turns off and starts really blocking the particles. And that's just for mathematical convenience. I could make any shape, and that's really important. But I'm just going to imagine that shape as we think about this experiment. Then what we can do is we want to determine then, the question is the state of the system, right? The state of a particle once it's just made it through this blocking filter. Now the first thing I can ask, of course, is where is it as it crosses this x-axis? So to measure that, one thing I can do is I can put in here, right, a photo plate, and I will call this photographic plate, or my photo plate number 1. And the goal of this thing is that this thing then gives us, by simply looking at how dark or light things are on this photographic plate, it gives us a direct measurement of the probability of where my particles land, right? It gives me, where they land on there, gives me the probability distribution in X. Very good. Now, I'm also interested, of course, in determining the probability distribution for the momenta, because I need to know all the different possible probability distributions. So to measure that, what I would do is I would remove my photoplate 1, which is this straight plate, and I'm going to put in a second plate, which I'll call photoplate 2. And just for convenience, I'm actually going to make this a circular plate. Photographic plate. So I'm trying to draw something here that's going to look more or less like a circle as best I can make it. Something like so. Oh, that is a pretty bad circle. I apologize for that. It's too parabola looking. Trying to make it look more kind of circly. Yeah, that's a little better, right? So this here was photoplate 1, was the straight plate. So let me indicate it like that. This here, this curved plate, this is photoplate 2. And that's a semicircle, so and it will have a given radius. And just for convenience, I will use the same radius r. And the idea behind photoplate 2, as you know, is that, well, then I can go and I can measure where my particles land, right? And then by looking at, for example, the angle at which they come out, theta, right? That will tell me more. That will tell me about their momentum in the x direction. I'm going to ensure for photoplate number 2 that the radius of this curved plate is much greater than sigma, which is the range in which the particles come through my filter. So I won't know where the particles came through my filter, although clearly they haven't come from further away from the origin than this distance sigma. Right? Where they land on this curved plate then is really not so much a function of this small range in which they've come through, but much more a function of the angle at which they are emerging. And we can use that then to determine, this gives, of course, some probability distribution for arriving at different angles theta. But the real point behind this is it tells us the momenta in the x direction of these particles in that quantum state I prepared for them just after they've gone through my filter. It tells the momentum in the x direction, which is the magnitude of the momentum times then the sine of the actual angle at which they've landed. Very good. And by ensuring this r is much greater than sigma, I want you to notice I've also ensured that the brightness of my source, even though some points on this screen might be closer or further from the source because the source is very far away compared to sigma, right? The distance from my source to any of the points that make it through that filter is almost the same. So the brightness coming from my source in the relevant regions here is going to be constant. Very good. So that's the basic setup that we're going to use. And what we want to do now is to begin to explore what this can really teach us about the relationships between the probability distribution for the momenta in the x direction, right? And how that may or may not be related to the probability distribution in x. And that's what we are going to take up in our future discussion.